Okay, let's go back to, here's the last problem that we looked at. And I've got some, Lucy, you've got some explaining to do. All right, consider a cylindrical cable with a hanging weight suspended from it. All right, consider this. And I don't think I put in a lecture or in our notes or on YouTube, I don't think I created a lecture where we talked about the Young's modulus, and I apologize for that. So here's what we're doing. We've got a cable coming down here, and it's hanging, and it's right here, and it's hanging, and it's holding some cylindrical thing like this, all right? And so we have mg pulling down. So we have this force pulling down. At this point, we have a force pulling down. Of course, the tension is also pulling up on that point, but we're just looking at the force pulling down, all right? And this is a stress is equal to strain. That's what the Young's modulus thing is all about. And the stress is equal to the force divided by the area. Stress is also related to pressure. It's the same thing as pressure. All right. And then we have this Young's modulus, Y, for a material, and that's material dependent. Okay. The Young's, that's what we're talking about, Young's modulus. That's what we're saying. And that's equal to the change in the length divided by L naught. So this thing got stretched and it changed its length. Okay? And they want us to find Y. All right? That's what's going on here. One other thing, Hooke's law. Hooke's law says this, that the force pulling down on this, if it stretches this string, all right, so it stretches it from here, say to here. So this is the old one, and now it's new, and this is delta L. I always use delta L. Where delta L is equal to L1 minus L naught, the stretched thing, right? Hooke's law says F is equal to some spring constant, K, times delta L. That's for the second part. And we're going to come up with an expression for K based on what we get here. All right? All right, so here we go. And we discovered something very interesting in class, which I thought was pretty good. All right, so what's given here? We know that L naught is equal to 4.59 meters. We know that L1 is equal to 5.26 meters. And we know that the mass is 55 kilograms, and that the area of the thing is, or the radius of the cross. This area is the cross-sectional radius of the string. Okay, it's the cross-sectional radius of the string, and that R is equal to 0.035 meters, where the area then is equal to pi times R squared. Okay? Sorry, you couldn't see what I was writing there. Probably poor quality video there. So anyway, so what we got to do is we got to find Y. All right, I can find Y because I've got numbers for everything else. I know that the force, this is all explanation for up here. So the force here is equal to mg. Okay. So we're just solving for Y, and that's just a algebra thing. So we've got, when we solve for Y is going to equal, multiply both sides by L naught, and divide by area times delta L, which is L naught minus L1 minus L naught. which is delta L. That's the way I do it. So there we got everything for y. You know what you know what the force is. The force is equal to mg. Okay. L naught we've got. You can find the area using pi r squared. So you found y. Now their next question that they have here is kind of interesting. It says if we were to double the radius, okay, what would happen to the young? What would if we were double and rhesus? Which of the following would be correct? Okay, Young's modulus would. Now remember, when you double a radius, so here's what happens. Now we take r prime is equal to 2r. When I square r prime is equal to 4r squared. So I'm dividing by 4 here. I'm now dividing by 4, which is reducing it by a factor of 4. All right. So what are we reducing? Can we reduce the Young's modulus? No. No. The Young's modulus, y, never changes. That's just what the thing is. That's just a physical attribute of the object. Never changes. Okay? So would increase. No, nothing here is increase. Oh, so the only other decrease that we have is this one. And yes, the stress will be reduced. The stress will be reduced by a factor of 4 because now we've got 4r squared here in the numerator. Okay, from this 4r squared here, put it up here in the numerator, boom. So this one is yes. And then by Hooke's law, since Hooke's law is equal to F, which is equal to mg, k times delta L, so we're going to use Young's modulus. So is there a way to find delta L using Young's modulus, which is this L1 minus L2, okay? To get it by itself, okay? Yes, we can. All right, so it says, if the cable is pulled down a distance d from equilibrium position, it acts like a spring when released. When an expression determines the spring constant k, it says write an expression for the term constant using y, a, L naught, and r provided in part A. Okay, so we can write an expression for k using the Young's modulus. So I know it's going to stretch a distance delta L. All right. I know it's going to stretch this. So, but we've got to find, well, what does k equal? What does k equal? So what I'm going to do is I'm going to take this F here and set it equal to k times delta L. Okay? And then take it from there and then solve for k. That's the simple thing that we're going to do. It's where delta L is now equal to D. Can we use D? It stretches the distance D. Okay. But we can just use this delta L. All right? I'd be confused. So let's just take a look at it. Here's what I'm saying. Whoops, don't want to put it on the back. We'll put it on the front here. So here's what we've got. We've got Young's modulus, or Hooke's law says K equals force constant, or spring constant times L1 minus L naught. Okay? And I've got the Young's modulus equation, which says F over A is equal to Y times L1 minus L naught over L. Okay? So I've got to write an expression for K. So I'll just take this F, stick it in here. I get K times L1 minus L naught over A is equal to Y times L1 minus L naught over L naught. Okay, should make this L naught. Clear on that. All right, look, this term cancels. And so K is equal to YA over L divided by L. So you can write that as YA over L naught. Okay. Did they allow for us to use the A part? The variable A? No, they did not. No, they did not. So you've got to do this. Y pi r squared over L naught is equal to K. There you go. All right. That's good.